Is it okay?
Yeah, please go on, please go on.
Okay, thanks. Thank you very much for the invitation. I really appreciate. So today is going to be about what I call quantitative orbit equivalence, and this is going to be a joint work with Thibaut Delaby, Ioannis Koivisto, and François Lemaître. Okay, so let me start defining the object of study. I'm going to restrict a bit more the topic than what was in the abstract. I'm sorry about that, but I think it's going to be more focused, and that's probably a better thing. So I'm not going to talk about measure equivalence, but just stick to orbit equivalence. So the main objects that we are going to study in this talk are going to be these three things that you can see the list on this slide. So the first object are countable groups. So you may think of Z, ZD, or free groups on finitely many generators, let's say. Although we are going to focus on amenable groups, so mostly Z and ZD and other examples that we will see later on. The next object will be a probability space. So you may think of, two basic examples that there will be standard probability spaces. So you may think, for instance, of the circle equipped with the Lebesgue measure, or the infinite product of 0, 1, where, for instance, you put the probability, the product probability, which gives 1/2 to 0 and 1/2 to 1. And finally, the central object will be what we call probability measure preserving action. So we abbreviate it by PMP. And we are going to assume that these actions are free. By free, I mean the following. So we'll say that an action will be called free if for almost every x in X, the set of elements in gamma that fix this element is simply the natural element. Okay, so that's almost the same as saying that the action is free, except that it's essentially free in the sense that it's in the sense of the measure. Okay, and another condition that I didn't write down, but that's going to be often in the assumptions is ergodicity. So ergodic is a kind of minimality assumption, because it says that whenever you have a subset of a measurable subset, which is gamma invariant, then the only possibility for its measure is 0 or 1. Okay. So for instance, if you take two such PNP options and you take the disjoint union of them, that it's no longer ergodic, basically. So this is why it's a kind of minimality assumption. So examples of such things are, basic examples are, for instance, you take an irrational rotation on the circle by Z. So why do we take irrational? Because if it was not irrational, then it would not be free. Okay, because it would have finite orbits. But if it's irrational, then it's free, and it's easy to see and well known that it's ergodic. And another example is what's called Bernoulli shift, which is an action that can be defined for any group, any countable group. And it's simply the action of lambda on this space that I already described, 0, 1 to the, all the functions from lambda to 0, 1, measurable functions. So equipped with the product measure. And of course, the action of lambda here is by translating, by shifting. So these two actions are well known and very interesting to study, and they are ergodic. Okay, so now I'm going to describe orbit equivalence, but before I'm doing it, I'm going to again tell you something about this object that we have just defined. So first, before introducing orbit equivalence, it's important to introduce the natural notion of being isomorphic between two such things, between such objects, okay? So naturally, if you have an action of gamma on x mu, a PNP action, as I define, and another action lambda on y nu, what does it mean for them to be isomorphic? Well, in order to have an isomorphism, you need to have, of course, an isomorphism between the spaces. Which is a measure space isomorphism, probability space. Which means that it preserves the measure, that it's essentially bijective and so on. And you also need an isomorphism between the groups. Okay. And then, of course, you need some compatibility assumption between them. And the compatibility assumption means, of course, that psi is supposed to transfer the action of gamma to the action of lambda through the isomorphism phi. So this precisely means the following: for every gamma in gamma, and for almost every x in x, you'll have that psi of gamma x is phi of gamma times psi of x. So this is the compatibility assumption. So let's take a look a little bit at this condition. So of course it's very strong. It's very strong, but it's not so evidently strong in the sense that it's not, for instance, so easy to see that these two actions that I showed you, like this action S1 and this action on the Bernoulli shift for Z, let's say, even if you have the same group, it's not so easy to see that they are different, but it's true that they are different. So for instance, these two actions that I gave you here are not isomorphic, but it takes some effort to show it, okay? It's not something so trivial. So the study of PNP actions up to isomorphism is far from being a trivial subject, okay? And it involves the study of entropy and so on. So that's not going to be the main goal of that talk. But the main defect for us with this notion is that it forces the groups to be isomorphic, okay? And our point at some point in this talk is to compare groups, is to forget about the actions in a way and to keep an information on the groups. So for this reason, this isomorphism notion is not interesting to us because when two actions are isomorphic, the groups are isomorphic. So in order to relax this assumption, we are going to essentially stick to the previous definition, but forgetting about the isomorphism between the groups. And so what's left? Well, if we do that, we see that we keep an isomorphism between the spaces, but we don't want to say that the groups are the same. But in a way, we want to say that the actions are the same. So what we just remember from the action is the equivalence relation generated by the action, namely the orbits. We want the orbits to be the same, okay? So this is precisely the definition. So you want that psi maps gamma orbits to lambda orbits, or here it's the other way around. So lambda orbits to gamma orbits, okay? And then comes a very surprising result by Dye from the late 50s, that if you take any two ergodic PNP actions of Z, then they are orbit equivalent. So for instance, I told you before that the rotation and the Bernoulli shift were not isomorphic, but they turn out to be orbit equivalent for the same group, if you take Z in both cases, okay? And that's a bit surprising because they look really different in a sense. By the way, here you ask the actions to be ergodic because it's clear also that the orbit equivalence preserves ergodicity. So of course you have to have this assumption here. So in order to go one step further, what we want to do now, because we know that all the actions of Z are the same, we may ask whether an action of Z2 and an action of Z could be the same, okay? So there is a class of groups which is very important, and the notion of amenability does not only appear in group theory, actually. It appears in many, many fields. In operator algebra, it appears in many, many fields, and I'm sure most of you have heard about this notion, maybe in different contexts. So basically, the idea of amenability for groups, let's say, is that it's a way to say that a group is almost finite or approximatively finite in a way. Because finite could mean that there exists a finite subset of the group which is invariant. Okay, if you have a subset, a finite subset which is invariant in a group under translation, then your group has to be finite because the only subset which is invariant is the group itself. Okay, so now if you want to relax the notion of being finite defined in this sense, having a finite invariant subset, well, what you come up with is a sequence of almost invariant subsets. So here we go. So you have the following definition. A countable group is amenable if it has a sequence of almost invariant finite subsets, namely a sequence of finite subsets an, such that for every lambda in lambda, the symmetric difference, the renormalized symmetric difference, size of the symmetric difference, sorry, of an with an translated by lambda tends to 0. Okay, and so this is called actually a Følner sequence, and here right because we translate from the right. So, and a Følner sequence because it comes from Følner, who introduced this equivalent definition of amenability, because there are many, many different definitions of amenability, which are all equivalent. So examples are, for instance, Zn or Zd here. Let me just very briefly explain for those who are not used to this. For Z, when you want to take a Følner sequence, so you think of Z as a line. Of course, it's a discrete line. And what you can take is, you can take an interval minus nn. And what clearly happens here is that if you translate it by 1, then what you see is that this interval is mapped to this one. And so the symmetric difference, which is this part here, and this part here, is clearly small in comparison to the whole thing. If you take, so this is an. So if you take an plus 1, translated by 1, symmetric difference an, divided by an, here you see that this is exactly 2 because the number of points which are in the symmetric difference, there are 2 points, one on both ends, divided by the size of the interval, which is 2n plus 1. So of course it tends to 0. If you want to consider Zd, you just take a finite product of these and you would still have, let's say for d equals 2. And again, you would have the same thing that if you translate it by any element, the symmetric difference will tend to 0 like 1 over n. Okay, and so on. So these are examples of groups which are amenable. Yes, and I'm also giving 2 other examples that I'm going to define right now, but I'm going to study them a little bit more in details later. So sorry, let me come back to this whiteboard. So the Heisenberg group over the integers is the following group. It's a group of matrices which look pretty much like an abelian group, but it's not. It's a group of unipotent matrices with 3 parameters, x, y, z, that belongs to z. And it's almost like z cubed, okay? But it's not, of course. So an interesting fact about the Heisenberg group is that it fits into a short exact sequence. So what happens here is that if you take the group generated by or when I said Z, what I mean precisely is this element. Okay, so this element is central. It commutes with everybody else. Okay, and so you can, of course, it defines a normal subgroup, so you can mod out by this normal subgroup, and then when you mod out, then you are left with x and y that commute. Okay, So that's an extension of Z and Z square, and we know that amenability is stable on the extension. So in particular, Heisenberg is an amenable group. Later on, we are going to see explicit Følner sequences, but right now, just the fact that it's an extension of two amenable groups suffices to show that it's amenable. I'm going to describe a last example, which is the lamplighter. So algebraically speaking, the lamplighter is the following group. It's the direct sum indexed by Z of copies of Z mod 2. Semi-direct product with Z, where Z acts by shift. Okay? And it's common to describe the lamplighter in a nice pictorial way, where we draw a line, which is Z again. On top of every point on Z, you draw a lamp. Sorry, my drawing is not very beautiful. And so on. So you draw one on each one of them, and so on. And so here, let's say that the position is 0. And so an element is going to be a pair of two things. It's going to be omega, which is going to be a sequence of 0 and 1, indexed by Z, and an element M. Okay, and the idea is that somewhere lies a lamplighter. Okay, at a certain position, M, there is a lamplighter. Okay, and so the idea is that this pair of things, like M is going to be the position of the lamplighter, and omega n, the sequence of 0 and 1s, is going to tell you when a lamp is on or off. So some of the lamps will be on, some of the lamps will be off. Okay, and the idea is that the lamp is on if you see a 1, and it's off if you see a 0. Okay, and so okay, well, it's just a convenient way of thinking about this group if you are not used to it. But I'm not going to say much more about it. Let's come back to our more serious things. So here we have these examples. So I didn't say it, but the lamplighter is also an amenable group, because also it's also an extension of Z with an abelian group. So here it's not a finitely generated abelian group, but it's abelian, and being abelian, it's easy to see also that it's amenable. Okay, so these examples here are amenable. Now there are counterexamples, like the free group, for instance, and any group that would contain a free group as a subgroup on at least 2 generators is not amenable. Okay, I do not have time to explain that, but I mean, if you are used to it, it's a well-known thing. Okay, so why am I introducing amenability here? Well, because it's going to play an important role in this talk. And the reason is the following. It's a theorem of Orstein Weiss. Theorem of Orstein Weiss that generalizes the theorem of Dye that I mentioned previously. Dye was about all PMP actions, ergodic PMP actions of Z. Now, Orstein Weiss is about all ergodic PMP actions of any infinite countable amenable group. Okay, and the theorem is just the following. It says that two amenable groups, infinite amenable groups, are any pair of PMP ergodic actions of amenable groups are orbit equivalent. So in particular, if we want, as I explained a bit earlier, if we want to forget about the actions and just remember some information about the groups, say that the groups are not far from a certain perspective, then we use this definition here, which says that two groups are orbit equivalent if they admit a pair of orbit equivalent PMP actions. It do not necessarily mean that all pairs of periodic actions are going to be orbit equivalent, because you may have a group that has two non-orbit equivalent PMP actions, so it's a little bit weaker. But the idea is that you want to say that in a way you can relate a group and another one through actions, okay, that they can share same action, essentially, in a way, okay? So this theorem of Orstein-Weiss is very disappointing because it tells you that there is nothing to see really there among amenable groups. Like they are all the same, they define all the same actions, okay? And that's really something that sounds like a bit annoying in a way, okay? On the other hand, the situation for non-amenable groups is completely at the opposite. So there has been a lot of work, of course, because amenable groups were shown to be so uninteresting in some way. All the work and all the effort has been put on non-amenable groups for which a lot of rigidity has been proved. For instance, one of the most beautiful ones is a theorem by Gaboriau, who showed that if you take two free groups with different number of generators, they are not orbit equivalent. Okay. So it triggers the following question. Is this really the end of the story for amenable groups? Like, have we said everything interesting when we have said that, well, they are all defining the same orbit equivalence class?
Can I ask a question?
Sure.
This is Rigdisha. I want to know the theorem of Orstein and Weiss. What are the exact conditions? Are there any conditions? They're just two countable amenable groups.
There is no condition at all. You take, it's exactly as it is stated. So you take just two infinite countable amenable groups. You take any pair of ergodic free. PMP was freeness was encoded in the was supposed in the assumptions. So you take only any two. Let me give you an example, just to show you how general it can be. Like you take, for instance, Z acting on S1. Sorry. Acting on, let's say, the Bernoulli. Well, these two are orbit equivalent. And the only thing which is important here is that these two actions are ergodic, they are free, and the two groups are amenable. But of course, if you take Z acting on even the Bernoulli, or any action of Z, and you take the free group, then there are not OE. And the reason is something that I didn't mention, which is a theorem which is well known too, is that amenability is recognized by orbit equivalence. So if you have a group which is amenable and another one which is not amenable, they are never going to be OE.
Thank you.
Okay? So that's an example, the concrete example where groups are not OE. You're welcome. Thank you for your question.
One more quick question. In the definition of orbit equivalence of two groups, do you need the action to be ergodic as well? It's free, obviously, in the PMP action. But
you don't, because with this definition, if you have a pair of actions which are orbit equivalent, you will also find an ergodic one.
Because you'll go to the ergodic component. Yeah, okay.
Yeah, exactly.
Okay, yeah. Thanks.
Thanks. So, okay. So here is the picture, if you want. The picture about orbit equivalence.
Excuse me, hello?
Yeah.
So, your definition of this isomorphism.
Yes.
So, orbit equivalent, the definition, your group has to be isomorphic? What was the definition?
No, absolutely not. That's the point. With the orbit equivalence definitions, you relax the assumption that the groups have to have anything to do with one another. Because you forget about the isomorphism between the group. That's the difference with the isomorphism equivalence that I defined before, is that you just keep the isomorphism between the spaces. You forget about the isomorphism between the groups, but you keep something about the compatibility. Okay, and the compatibility only tells you that it has to map orbit to orbit. Okay. That's why it's called orbit equivalence. So you forget about the groups, really, but you remember the orbits.
Fine.
So yeah, so if we want to answer, so my question was, is it the end of the story for amenable groups? And of course, the answer that I want to give is no. Is no, but if we want to have a negative answer, we need to do something. We need to change a little bit the definitions. And in particular, what's important that we need to quantify orbit equivalence. What I mean by that is that it's true that an orbit, there is always an orbit equivalence between z and z squared. But how difficult is it? Like, how distortion do you have to do to pass from z to z squared in doing so? What I mean by that is that this conclusion of Orstein Weiss tells you that no geometry survives under this equivalence relation, nothing. But it may have a cost to transform a z action into a z2 action, and even more cost to change a z action to a z4 action, or to a lamplighter action, because the groups are so different. And we want to measure that. We want to measure how expensive it is to do it. And to do it, we quantify orbit equivalence. We just add we just measure how hard it is to do it, okay? And at the same time, in parallel, we are going to quantify amenability. And the reason is what? The reason is that we are going to try to put in parallel the fact that two groups are going to be differently amenable, like one is going to be more amenable than another one, with the fact that it's going to be hard to construct an orbit equivalence between them. Okay, the more the groups are going to be different from this point of view of being very amenable or not, the harder it's going to be to construct an orbit equivalence between them. So that's essentially the program that I'm going to try to lay out. So in order to do that, in order to measure all these things, you need to bring back some geometry. And this is the great comeback of geometric group theory, if you want, in the picture. So Orstein Weiss tells you that there is no geometric group theory, but we can bring it back to the picture. And in order to do this, we need to define very quickly something that I'm sure everybody knows, but I'm going to do it anyway, shortly, which is the word distance. Here, of course, we are going to focus on finitely generated group for the sake of simplicity. So you are assuming that you have a group which is generated by a finite subset, and we define the word length, which is, well, basically like a norm. You may think of it as a norm. It measures the number of elements in S you need to multiply to write down your element, okay? And there is a left invariant word distance, which is defined by the norm, or the word length of g minus 1 times h. So this formula only means that what you are measuring when you are looking at the distance between g and h, you are measuring how many elements in S you need to multiply g on the right to get from g to h. Okay, and that's left invariant because you're multiplying on the right. Okay. So once you have this, you can start doing geometric group theory, but you can do also something about our actions. Because you see that if you have x mu, a measure space, equipped with an action of lambda, and if you have a distance on lambda, then you can push this distance to x in the following way. So you can make x not only a measure space, but a metric measure space. And the idea is simply to say that 2 points have distance n if you can go from one to the other by just acting by an element of size n in your group. And of course, then when points are not in the same orbits, they are going to have infinite distance. So we are just not worried about the fact that our distance can take infinite values, which is really not a big issue here. So what we are having now is a distance that kind of that's going to be finite whenever the elements are in the same orbit. It's going to be infinite otherwise. And when the groups are in the same orbit, it's going to measure the distance in the group. Okay, so every orbit, if you want, will be identified with a copy of the group equipped with this left invariant distance. Okay, and now it's interesting to see when you have two groups acting with the same orbits, which is what happens in orbit equivalence. When you have two groups that are orbit equivalents, then through the isomorphism between the measure spaces, you can assume that you have a single measure space, probability space, with two actions, one of lambda and one of gamma, as in my definition here. And they have the same orbits. So now you want to measure the distortion. What I mean by distortion is that if you had an isomorphism between lambda and gamma, and you had an isomorphism between these actions, well, then you would have essentially that the two distances would be the same. Okay, you would pick the same generating set for both groups, which would be the same group, and you would get the same distance. Okay, but if you have two different groups and with two different actions, even if it's the same group, but if you have two different actions, then whenever you translate by one action, through one action, if you move through one action, for instance, you take a lambda in lambda and you move x to lambda x, you know that there exists a gamma such that you could do the same with this element in gamma. But the length of this element in gamma may fluctuate, maybe very large, for instance, you see. And so in order to put some constraints on this orbit equivalence between these two groups, what we are going to use the measure to integrate the distance. When you translate by an element of lambda, you are going to measure the distance with respect to the gamma distance, and you are going to integrate. Okay. And then you can start putting some constraints. For instance, you can ask that this distance is p-integrable, but you could also ask that it's bounded. Okay. And just to make sure that, just to explain this thing, I'm going to explain what happens if they are bounded. So the case p equals infinity is interesting. So the case p equals infinity means that for every lambda, or let's say for every s in s lambda, you have that the integral, no, not the integral, sorry. You have that almost surely, you have that the distance measured with gamma, sorry, S gamma, of x s x is finite, so it's less than a constant. Okay, so there exists a constant c. And you have the same thing. You have for every t in S gamma, you have that AS, you have the distance between x and tx is less than c. And here is for S lambda. Okay. And if you think about it, well, this implies that if you look at every orbit, this means precisely that the two distances are the same. So this implies this equivalent to the fact that ds gamma is for almost all x in x. Why? Because you have two situations. Either the x and y are not in the same orbit, so it's infinity, so nothing too interesting. And if they are in the same orbit, then by the previous inequalities, and using the definition of the word metric, what you will have is that the distance will be essentially the same. They will be equivalent. Okay. So in particular, of course, this has a very strong consequence on the groups, because what you are writing here is that the groups are actually bi-Lipschitz equivalent. So they are even more than quasi-isometric, if you want. They are bi-Lipschitz, so they must have the same geometry. So if I come back to this notion here, having an L.
So Romain, someone has a question.
Yes.
Yeah, actually, I'm just a bit confused. You see, when you're taking this distance,
yes,
that ds gamma x lambda x p, isn't it just the norm of lambda? The distance on top is given as just lambda. So doesn't it become a constant for a fixed lambda or what?
it doesn't have to be a constant, because you see what happens is that what's happening is the following thing. You have your space X, okay, and you have X in X. Okay, so this is a point on your space. Let me draw a picture instead. So this is X. Okay, here you have an orbit. An orbit means at the same time an orbit for lambda and an orbit for gamma. Okay, you pick X in this orbit, and you multiply it by lambda. So it's mapped somewhere. Okay. But now you know that because you are in the same, because the orbits are the same, so gamma X equals lambda X. If there is a way, I mean, there is also a gamma. Okay, so there exists. So just to simplify my exposition, let me just suppose that this is a generating set. Okay, so it is a small element if you want. Okay, it's an element of length 1. So when I map X to Sx, I know that there exists, because they are in the same orbit, I know that there exists some gamma. Okay, that depends on X. Okay. It depends on X, and it also depends on S. Such that you have okay. So here I'm writing the gamma action in red and the lambda action in black. So here I'm sorry. Here I'm using, I'm acting through this element S in lambda, and above I'm acting with this element gamma, which is in gamma, and I know that they are doing the same on this particular element. Okay. So now what I'm measuring is, so I know that S is a small element, it has length 1 by construction. Okay. But then the element that lives now in gamma, that does the same job, what is its length with respect to gamma? You know, if it's L infinity, then it means that this length is bounded. And if it's L1, for instance, it means that it's integrable with respect to X. So you see, it measures the distortion, because if it is bounded on both ways, then it means that this map, it means that the distance with respect to gamma or the distance with respect to lambda are by Lipschitz. Okay, and so that gives you that this map, if you fix X, the map that sends lambda to what I called gamma X lambda. It's a map that goes from lambda to gamma. Okay. X is fixed, so it's really a map from lambda to gamma. It's called the cocycle. I didn't want to introduce that, but the idea is that this thing, it depends, you have to fix a point in order to identify an orbit, and then you have a map from lambda to gamma. It's not a morphism, because we do not have assumed that you have the national morphism, but it's something that, it's a map. Let's say it's a map. And here what we are doing by considering the length is we are measuring how far this map is from being a bi-Lipschitz map. How far is, how much distortion this map creates in terms of metric. Does it make sense?
Yeah,
it's quite an important notion, so I'm not against spending time on it.
Yeah.
So
but is it dependent on the, is it if we change the generating sets on both sides?
Okay, you're making a very good point here. So the point is that this is not going, I mean, the condition of being integrable is not going to be affected by a change of generating set. Because a change of generating set is only changing the distance up to a multiplicative constant. So this is not going to affect the fact that it's L infinity, L1, LP, and so on. Okay, but that's a very good remark. And that's the whole point of geometric group theory, is that geometric group theory, you fix a distance, a word distance, but you don't really care in the end, because whenever you change the distance, you know that you are by Lipschitz to your original distance. It's only up to multiplicative factor. So all the notions that we are studying in geometric group theory are asymptotic in the sense that we only care about asymptotic behavior of things, so that it's not going to be dependent on the specific generating set that you're picking. That's quite important, and that's an important remark. Thank you for the question. Okay, so if we are okay with this notion, I'm going to define a slightly more general notion very, very shortly. So, but first of all, I'd like to make a comment on this definition. So as I kind of said it, the strongest possibility here is for L infinity, because it said that the two distances are basically comparable to one another. So what it suggests that for P large, it's more demanding than for P small. And indeed, it's easy to see that because you are integrating over a probability space, P integrability is stronger as P becomes larger, okay? So L infinity is essentially being by Lipschitz. So it's not being so much studied because it's basically the study of amenable groups up to quasi-isometry, if you want. So that's a different topic in a way. So people have studied L1. For some reason that can be understandable, but can be also questionable in a way that L1 is maybe not, more natural than anything else. Like LP, actually L2 has been studied too, a little bit. So here is the main point of what's going on. So as soon as you add L1, you start seeing some geometry coming back. So for instance, so I remind you what's the growth, which is the first asymptotic invariant that you want to define in a group, which is the size of the ball of radius n for the word distance. Okay, so for ZD, for instance, it grows at ND. Well, the first theorem by Bowen is that the growth is preserved by L1 measure equivalence. So that's a very strong result, because what it implies, for instance, is that although Z and Z square are orbit equivalent by Orstein Weiss, it's not L1 orbit equivalence. Namely, whenever you have two Z and Z square acting on the same probability space, some distortion have to occur. You cannot have integrability, you cannot have L1 condition, okay? So later on, we are going to see a much more refined version of this theorem, which tells you exactly what condition has to be satisfied by the coupling, by the two actions, so that you can have an orbit equivalence between a pair of such groups, okay? Later on, Orstein showed the following thing. So in order to understand why this result of Orstein is interesting, I need to explain a few things. By the way, can you just tell me how much time I have? I forgot to see my watch.
Like 12 minutes.
Okay, so I'm going to be a little bit fast. So what's important here is to understand this Heisenberg group. remember the Heisenberg group is this group. I'd like to tell you a little bit about the geometry of this group. So if you take S, a generating subset, this is a generating subset for Heisenberg. In order to generate the Z, which is above, you just need to take a commutator of these two guys, okay? So this thing, so let's call this guy big X and let's call this guy big Y, okay? Well, something interesting is that it generates all the groups and there is a fundamental relation, which is this one. If you take a commutator of X to the N and Y to the K, then you get Z to the NK, where of course Z, you have guessed, is this element here. Okay? And so this relation tells you what should be the ball of radius n. And the ball of radius n is the following. Like, it's not exactly the following, but Kn, if you define Kn to be if you ask X and Y to be less than n, because of this relation here, you guess that the inequality that should be satisfied by Z is not less or equal than n, but less or equal than n squared. Because if you take just a word of length n, you are already able to go to at n squared in the direction of the Z, in the direction of the center, okay? So this is not exactly the ball, it would be too good, of course, but the ball is comparable to that. So what happens is that if you want to, the ball, if you want, I'm sure I'm going to say it wrong, but it's contained, if I'm not wrong, in Kn, and it contains K, or let's say, I'm going to put a 4 here. We have something like that. So what is important is that it gives you enough information to tell you the size of the ball. It grows like n to the 4 because you have a contribution of n for X and Y and a contribution of Z of n squared for the Z. So it grows like Z4, the same growth as Z4. So now this explains the interest of this theorem of Orstein. You see that Bowen cannot distinguish between the Heisenberg group and Z4. But Orstein has a more general theorem than this one, but this one is an easy to state version of his theorem, which tells you that if you start with an abelian group, then if you are L1 OE to it, then you have to be abelian yourself. Actually, you have to be virtually isomorphic. Virtually means that there exists a finite index subgroup, which is isomorphic. So for instance, this implies that the Heisenberg group and Z4 are not L1 OE, okay, although they have the same growth. Okay, so now I'm going to go one step further. I define LP OE, and I'm going to just pick any function, okay, phi, and I'm going to ask my function phi to be increasing and to tend to infinity. So for instance, you may think of a logarithm function, an exponential function, an exponential of an exponential, a logarithm of an iterated logarithm, and so on. So a very, very slow function or a very, very fast function, okay? This is because we want to capture all the possibilities that may happen in Orstein Weiss theorem, okay? Because in Orstein Weiss theorem, there will whenever you have two groups, two amenable groups that are going to be orbit equivalent, there will exist a function for which your orbit equivalence is going to be phi orbit equivalent. It's easy to construct. There will always be a function such this one, increasing and tending to infinity, such that you will have this, okay? But the question is, what constraint can we put on this function? Okay, and this is what we are going to do now. So of course, the LP case that I defined before is a special case. It's only when you take t to the p for a function phi, okay? And again, we had that L infinity was stronger than L1, for instance, or LP was stronger than L1 if P was larger than 1. And here, what remains from that is that the faster phi tends to infinity, the stronger the condition. So exponential is very strong. It's stronger than LP for any P, except L infinity, of course. And logarithm would be very weak in a way, or iterated logarithm would be even weaker, and so on. Okay. So now we have a whole way to compare. Okay, so this is from the point of view of quantifying orbit equivalence. Now, what about amenability? So far, I described to you growth, the growth function. But the growth function is limited because many groups just have exponential growth function. The Lamplighter, I didn't have time to explain, but the Lamplighter has exponential growth, and all the solvable groups, almost all of them, have exponential growth. So, you know, Bowen's result cannot really help you so much in deciding whether these groups are going to be OE with good integrability conditions or not. So we need a more refined notion that is going to stick better with the definition of amenability. Let me come back to amenability. Amenability was defined like that. It was the existence of a sequence of finite subsets such that the symmetric difference tends to 0 when you act by an element, okay? So that suggests a way to quantify. And this is what's called the Følner function, which tells you what's the minimal integer for which you can find a set of size this integer, such that the symmetric difference is less than 1 over n, okay? So that's one way of quantifying how amenable you are. So the faster the Følner function is, well, the less amenable you are. Because in particular, a group is non-amenable if and only if this Følner function is equal to infinity for some large enough n, okay? So the group is amenable if and only if it is finite. And of course, it is more amenable if it's slower. The slower it is, the more amenable, okay? And the case of Z, for instance, Z is simply n, okay? Just n to the d. Actually, there is a general inequality between the volume growth and the Følner function. The volume growth is always less than the Følner function. And in many instances, they are the same. Like the Lamplighter, for instance, is going to be exponential, both of them. And for Heisenberg, it's going to be n to the 4, because they are going to be the same. Growth will be the same as the Følner function, okay? So now the interest of this function is that it's a much more refined invariant in the sense that we can distinguish many examples of groups with these Følner functions. We have solvable groups with extremely fast Følner functions. It's not like for the growth, which is just exponential and that's it. Here you can have exponential of exponential of exponential. It can be extremely fast, okay? So, and also it's very well known. It's been computed in many instances. So now comes our main result, which is the following. So first of all, we have a theorem which looks like Bowen theorem. It tells us that if two groups are L1 OE, then the Følner sets are the same. The Følner functions are the same. Okay, so that's the first result, which looks like Bowen results. But something which I think is more interesting is the second statement. The second statement is saying something which is stronger on the one hand, but which is also much more interesting. And it also applies to the volume. Okay, it says that if you have a phi OE for a concave increasing function, like for instance, logarithm or t to the p for p smaller than 1, then you don't lose everything. You know that there is a constraint between the Følner functions. Okay, and this is the way it's stated. So here you see that if phi is very slow, which means that your condition on the orbit equivalence is very weak, then the inequality here is very loose, because if phi is slow, phi inverse is fast, And so this inequality tells you something which is weaker. On the other hand, if phi is very close to being linear, is almost linear. If it's linear, then that's it. Then it's just the first statement. If it's a little bit below linear, for instance, if it's a power of, it's a t to the power of 1 minus epsilon, for instance, then it's going to give a strong condition on the Følner functions. Okay, and the point is that the same thing works also for the volume, but that's just following essentially Bowen's original proof. Okay, we just insert Bowen's proof, if you want, in our more general setting, and we get this result as well. Okay. And why is it interesting to have this second statement? Well, we have these two corollaries, which I hope are going to justify the fact that I think it's interesting. Well, first of all, if you take ZD and ZD prime, well, now you can not only say that they are not going to be L1 OE by Bowen, but you can say something stronger. You can say that for any P which is strictly larger than D over D prime, where D prime is the largest one, then they are not going to be OE, LP OE. Okay, so here what I mean is that we are going below 1. P here is below 1, okay, because D is smaller than D prime. Okay. And what you say is that not only they are not L1, but they are not even L D over D prime, OE. And we are going to see later that this is optimal. Okay. Also, if one has exponential growth and the other one is Z, for instance, then we have this logarithmic bound. So you cannot have a coupling which has a better integrability condition than logarithmic, which is weak. Okay. So in particular, you can never be L1 or you can never be LP for any P smaller than 1. Okay. So that's pretty strong. And finally, here comes somehow one of the main goal of what we wanted to do. As I said before, when you have an OE between two groups, there is always a function phi for which it is phi OE. Okay, you can always cook up a function phi. That's not a problem. But here we can give a converse to that. We can claim that whenever you pick an amenable group and another, and an increasing function phi that tends to infinity, even if it tends extremely slowly to infinity, you will always find another group whose Følner function will be so different than the Følner function of the original group, then the two groups will not be phi OE. Okay. So what I mean to say is that because we know so much about this Følner function, we know groups which have Følner function that can be as wide as you want. You can always find another group which has a so wide Følner function that it's not going to be phi OE to your group. Okay? So that really gives you that Orstein-Weiss theorem. There is no quantitative Orstein-Weiss theorem, if you want. There is no function phi that will work for all groups. Okay. Okay, so I don't have so much time, but I think it's important at least to explain that this is only half of what we would really like to know. It's much less than half, of course. It's nothing. It's just the beginning of an investigation. But what I mean to say is that here we have a rigidity statement with this Følner function, behavior of Følner function under phi OE. It's rigidity because it tells you that phi OE remembers something about the group. It remembers something about the Følner function. Okay, some weak information about the Følner function. But now what we want to know is, what about the flexibility point of view? Namely, can I construct explicitly an orbit equivalence between two actions of Z and Z square, for instance? And how good can I make this coupling? How good can I make this orbit equivalence? How integrable can I make this orbit equivalence? And it's kind of funny because the way we proceed, so we found a way to construct explicit actions of both groups which are orbit equivalent. And we control pretty well the integrability condition. It's very concrete. Unfortunately, I don't have enough time to explain unless if you want to ask me during the question, but I won't have probably time to explain to you the precise construction, but it's a very, very explicit one, very explicit one. And the actions are not, the actions that we are constructing are not going to be exotic actions. They are what's called profinite actions. So they are actions which are reasonably well understood. So my point is to say that, of course, in Orstein-Weiss theorem, there is an existence result that tells you that when you have two groups which are amenable, you can find an orbit equivalence between them. So of course you may think, well, Romain, why are you trying to recover stuff which are already known? Orstein Weiss has done the work for you. You just have to take his proof, their proof, and find the good quantifiers, you know. But the point is that their proof is existential. It works for any amenable group. So it doesn't tell you anything. We tried with François to get some quantitative information out of it, but we could not. You know, it's really very qualitative in a sense. So I'm not saying that it's impossible to do it, but we couldn't do it. And also something important is that in Orstein-Weiss, it's for any pair of actions. Whereas here, we are only constructing specific actions for which the groups are, are well connected in a way, you know. Like we are not proving that for all actions of Z, for instance, there exists an action of Z square, which is good, if you want. Okay, so it's only for very specific actions. So quickly, how do we construct these actions? Well, the basic fundamental tool that we need is again related to Følner sequences. Okay, so but it's not this case. It's not just a sequence of Følner sets. It's a bit more. We need a bit more than that. We need a sequence of Følner sets which are paving each other. So if I draw a picture, a Følner sequence, a Følner tiling, looks like something like that. So at scale n, you have your Følner set Fn, which is paved by translates of Fn minus 1. So here, let's say that this is Fn minus 1, and you will have a paving. And so on. Okay. And then at the next step, you'll have, so this will be Fn plus 1, and Fn plus 1 will be again paved by translates of Fn this time. And so on. You see that there is some kind of fractal picture that is kind of displayed in this way. So let me just give you a very simple example where it's kind of clear what happens is that for Z, you may pick Fn to be just, I hope I'm not going to be wrong. It's going to be, I think, 0, 2 to the n minus 1, if I'm okay. Okay. And so what you see, of course, is that if you take Fn plus 1, then it's just 2 copies of Fn. So Fn plus 1, so Fn is going to be, it's going to be, I'm going to make a small picture. And so this is going to be Fn, and Fn plus 1 is going to be this one. I'm forgetting the minus 1 here. And of course, we will have 2 copies of Fn, so Fn and Fn plus 2 to the n. Okay, so one will be a translate. So this is going to be Fn. And here, a translate of Fn. This is just a one-dimensional picture of what I drew at the previous, my previous screen. Okay, and of course you can easily imagine what you would have for Z2 and so on. So this is the picture. Okay, this is the picture. And the point is that what happens is that you see that if you have two Følner tilings like that, such that you have that for every n, the size, only the size of the Følner, I have something I forgot to say, sorry. I forgot to say that Fn is not any set. It has to be a Følner set. So it has to have a smaller and smaller, it has to be more and more invariant under the group action. That's really important. Here you can see that in Z, I have intervals, large intervals. So large intervals are definitely Følner sets. Okay, they are more and more invariant under the group action. And so the point is that to construct an orbit equivalence, the only thing you need to know is that you have a Følner tiling for each group such that the cardinality of Fn is the same for one and for each group. Okay, it can grow, it can be constant. For instance, for Z, the cardinality is 2 to the n. Okay, so if you can do the same for Z squared, then you're set. You have an orbit equivalence. Okay, and so if you have this, then you can construct an orbit equivalence between the. You can construct two actions precisely, and you can construct an orbit equivalence. I mean, it's clear actually that the two actions are orbit equivalent. And what's interesting there is that you have a good understanding of the integrability condition satisfied by these actions. And the point is that how good is this coupling only depends on how good is the Følner set, the Følner sequence. And here it's measured in terms of decay of this relative decay of the symmetric difference on the one hand. So this has to grow to decay fast, and at the same time you don't want the diameter, not the size, but the diameter of Fn to grow too fast. Okay, and so if you can control well the growth of the diameter and the decay, you can have a fast decay, then you will have a good integrability condition, some good phi. Okay, and the point about this is that it gives in many instances this construction gives optimal results. For instance, for ZD, you remember that I told you before that with the isoperiodic profile or even the growth, you couldn't have an LPOE for P strictly larger than D over D prime. So here there is a gap because we don't know what happens at D over D prime precisely, but we know that we can construct an orbit equivalence for any P which is smaller than D over D prime by just this construction here. And more interesting is that you remember that by Orstein's result, which is a very refined result, we knew that Z4 and the Heisenberg, although they have the same growth, n to the 4, we knew that by Orstein, they were not L1 OE. But here, if we do this construction, we see that they are LPOE for any P smaller than 1. And finally, for the Lamplighter, we knew that you couldn't do better than log because they have, one has exponential growth and the other one has linear growth. And here what's happening is that with this construction again, you can get not exactly log, but you can get any power of log which is less than 1. So it's not far from optimal. Okay. And of course, there are many, many more examples, but these are, I think, at least the one I discussed during the talk. So I think I'm going to stop here. Thank you very much for your attention.
Thanks a lot.
Thank you.
Okay, so any questions?
Just a small curiosity, may I? Sophie here.
Yeah, please.
I mean, you gave a certain idea of the quantification of amenability, right?
Yeah.
And amenability is equivalent to the existence of so-called, those invariant probability measures.
Invariant means, yeah.
Invariant means, yeah. So is there a way to quantify those measures in some sense in terms of the quantification of the Følner condition for amenability?
Not that I know, because the invariant mean is like, the invariant mean is like passing to the limit.
Mm-hmm.
You know, when you have a Følner set, it's a sequence of almost invariant probability measures, actually, because if you think of the sets are almost invariant with respect to this measure here, which means that if you take the renormalized counting measure on these finite sets, it means that you have a sequence of probability measures which are asymptotically invariant.
Mm-hmm.
And the point is that when you just remember the existence of the invariant mean, it's like just passing to the limit. So it's saying that, okay, in a weak topological sense, there exists a limit which is now invariant, except that it's not a probability measure, it's a mean. Okay.
Mm-hmm.
So because of that, because it's a limit of something, I'm not saying that there is no way, but not that I see at least. I don't see any way to quantify it because it's too late somehow. You already passed to the limit. So you forgot about the process of convergence. And here somehow measuring amenability means that it tells you how fast you can converge to an invariant mean. So you could do it, but it would be cheating because it would mean that you have an invariant mean which is well approximated, if you want, by finite measures or something like that. That would be another way of redefining somehow the Følner profile or the Følner function.
All right. And how about the amenability of the Heisenberg over Rn?
Yeah, so if you switch to locally compact groups, you can also do the same theory. And you can do it for Lie groups, except that, of course, you have to take into account the topology. Here, at the beginning, I was requiring the groups to be countable. Of course, if you do not assume that the groups are countable, if you consider locally compact groups like Lie groups, then you have to add some assumptions on the actions. The actions has to be Borel and so on. It's a little bit, everything has to be restated in the correct way. But in terms of amenability, at least, if you think of Heisenberg over the reals equipped with an invariant distance, like for instance, a Riemannian invariant distance, then you can define everything. You can define the profile, you can define the growth, and they are going to be the same as for the discrete one, because the two are quasi-isometric, because one is a lattice inside the other, and so they have the same geometry. The large-scale geometry of the real Heisenberg group is the same as the large-scale geometry of the discrete Heisenberg group. Mm-hmm. So they have the same growth. They grow also like n to the 4. Almost whatever metric you put on it. Like you could take a left invariant Riemannian metric. You could take a Carnot-Caratodori metric, if you know what it is. You could take a world metric with respect to a compact generating set. You would always get the same answer, that the growth is n to the 4.
Okay. Okay, one last thing in the same circle of ideas. The Heisenberg on R is not Lipschitz embeddable into an Euclidean space. How about the Heisenberg over discrete?
It's not either, because if it was by Lipschitz embeddable, then you would have a by Lipschitz embedding of the rescaling guy. Oh, sorry. Okay. Well, it's because Heisenberg over the reals can also be seen as the rescaling limit of Heisenberg discrete under some, I don't know if you heard about that, but somehow you can see Heisenberg over the reals are some kind of limit of Heisenberg over the discrete, over discrete Heisenberg. And so if you have even a quasi-isometric embedding of the discrete Heisenberg, then you can deduce by passing to the limit a by Lipschitz embedding of the real Heisenberg.
Oh, I see. So it's not Lipschitz embeddable.
No. And that's a very good question, actually. So you're right that you know that this Austin versus our result for Heisenberg and Z4 is kind of interesting from this point of view, because it's a measurable way of measuring how close to by Lipschitz the two groups can be. Mm-hmm. Austin tells you that it's not by Lipschitz in the integrable sense, like it's not L1. And we say that if you just go a little bit below, then it's fine. Statistically, okay. If it's statistically by Lipschitz in some sense.
Mm-hmm.
If you want, this quantitative orbit equivalent thing is like some kind of statistic by Lipschitzness or something of this kind. That's the way you may think of it. You measure the probability somehow that points are mapped at same distance.
Okay.
Parthanilda had raised his hand. Please, do you have a question?
No, it's okay. My question has already been answered. So that that's why I lowered it also. Thank you. Thank you.
Can I ask a question?
Yeah, please, please.
So one comment is, so are you saying that if the groups have same growth constant, then they would have similar behavior in terms of LP equivalence?
So not in general, but that's a good point that you are raising, because it depends a little bit on what kind of groups we are talking about. If we talk about groups which are polynomially growing, like ZD, for instance, or Heisenberg, or more generally polynomially growing groups which are nilpotent, then there is a result like that which I didn't state, which is just due to myself and to Delaby and myself, where we prove that the fact that if you have two groups which have polynomial growth with the same exponent, like n to the 4, n to the 5, or n to the 6, or whatever, then they are LPOE for any p less than 1. So that generalizes what we have for Heisenberg and z to the 4. But this becomes really false as soon as you leave this world of polynomially growing groups. For instance, if you take exponentially growing groups, most amenable groups are exponentially growing. But still, here, the isoperimetric profile distinguishes them really well, because among these groups that have exponential growth, some of them have like exponential isoperimetric profile, and some of them have extremely wide isoperimetric profile, like exponential of the exponential of exponential of exponential, how many times you want. So they can be as far as possible in terms of integrability of integral OE. Okay, you can have as bad as you want.
So you always know how to find a formula for this function?
So what we know how to do is using this result here, the theorem, the second line of the theorem, we know how to give a lower bound, no, an upper bound, sorry, on the phi for which you can be phi OE. Because the slower, the less demanding it is. So if we put an upper bound, it means that you cannot find better than that. You cannot do better. On the other hand, with this Følner tilings thing, we can find a formula that indeed is almost sharp for a whole family of groups. Okay. And so we have, like we can produce examples for which phi is almost the inverse function. I mean, it's an iterated logarithm, basically. And we know that it is sharp, almost sharp.
Yeah. I have one more silly question. Can you go back to your integration page? The integration.
This one?
Yeah. So you see, if you look at it, the function, the one bit, not phi, just the general function. Or
just
even
the distance.
If your phi is constant, then this ds gamma x lambda x, it's just the length of the word lambda, right? I mean, the metric lambda. So it doesn't depend on x, right? This was my confusion.
Can you repeat? Sorry, if you ask phi to be constant.
So x to lambda x, the distance is constant. Doesn't matter what x is, right?
If you put phi a constant function.
Yeah, you put phi equal to 1. Sorry, I have a plane going overhead. So.
I see what you mean. So if you say that phi is a constant whenever the variable is finite.
No, so here x varies, but this distance does not vary because lambda is fixed, right?
Yes,
and
exactly.
It's defined on the previous page as just the mod of lambda, word length of lambda. previous, yeah, see G of S, right? So distance between X and GX is just G of S.
Absolutely, that's a very good remark. That's a very good question. So let me explain. Oh, sorry, go ahead.
So that's my confusion. Here you see this is a constant function below in LP orbit equivalence.
Yes, it would be, but the point is that if you look at the definition, maybe just LP, what you see is that we are measuring, look at the formula very closely, you see that we are measuring the integral of, with respect to S gamma.
Yeah, below it will change, but above, I mean, there also it would be a constant function gamma, right? Isn't it gamma, mod gamma, right? Both of them are constant, right? Each of them is constant. They may vary, the constant may vary. But
no, but you see, it will depend on X. You know, like if you, in this formula, in the LP orbit equivalence, if you measure the distance with respect to gamma of X with lambda X, it will not be a constant because it will depend on X and on lambda. Because the only thing we know is that there exists a gamma that maps X to lambda X, but we don't know anything about this gamma. And what we are measuring here is the length of this gamma. And it depends on X, you know, it depends on X. That's at some point,
yeah, okay, I will have a look at your paper.
Okay, no problem, no problem.
Maybe you can elaborate. Maybe you can elaborate. I'm also curious about this. I'm also.
Oh, but then I will do it. Yeah. So it's my pleasure. This is what I try to explain in this picture. What I was describing in this picture is the fact that when I move through an element, here S was lambda. I'm just here picking, just for the sake of clarity, I'm just picking an element which is in lambda, but which lives in the generating set of lambda. Okay, so that the distance is not only constant, as you said, but it's one, only one. Okay. Now, when we are measuring the distance between X and S times X in terms of d gamma, and not about d lambda, d gamma, then what it means is that we are measuring the length of an element gamma that maps X to Sx. So this element, I call it gamma index X, comma S, because it depends on X and depends on S. It's an element in gamma. It depends on both data, okay? And so the point is that you see that indeed S has length 1. So in terms of d lambda, X and Sx, is 1. If you measure it in terms of, oh, I'm sorry. I cannot make a mistake here. It has to be lambda, okay? Because S is in lambda, so it's constant, as you were saying. If I'm measuring with respect to S lambda, okay? But now, if I want to measure it in terms of S gamma, then what I need to do is measure the length, not of S, but the length of gamma XS with respect to S gamma.
Okay.
And this is something that varies. Okay, it may change a lot depending on where you are. You know, even if you fix S, when you're fixing S,
yeah,
it may depend on X. You know, even along the same orbit, it may depend on X. A lot.
Now I understand better. Thank you.
You're welcome.
Very nice talk. Excellent. Thank you.
Thank you very much for your questions.
Okay, are there any further questions? Okay, so I guess we can clap and let Romain know our appreciation.
Thanks, Romain. Can we close the session? No?
Yeah,
sure. I would like really to thank you for all your questions. It was very, very pleasant to have this feedback from you.